600 amp service is not based on the full load amps of the equipment. It is based on the minimum service capacity required by the National Electrical Code, or NEC, for a system of this size. The NEC requires a minimum of 100% of the continuous load plus 25% of the non-continuous load. The continuous load in this case is 214 kilowatts, which is equivalent to 282 amps. The non-continuous load is 244 kilovolt amps minus 214 kilowatts, equaling 30 kilovolt amps, which is equivalent to 40 amps. 25% of the non-continuous load is 40 amps multiplied by 0.25 equaling 10 amps. The minimum service capacity is therefore 282 amps plus 10 amps equaling 292 amps. However, the NEC requires that the service capacity be rounded up to the next standard size, which is 600 amps. Yes, the service wire should be sized based on the bus plug rating. The NEC requires that the service wire be rated at least 125% of the bus plug rating. In this case, 600 amps times 1.25 equals 750 amps. To figure the service cable to the machine based on the bus plug rating, use the following formula: service cable size equals bus plug rating times 1.25 divided by conductor ampacity times conductor dirting factors. Conductor ampacity is the ampacity of the conductor at the operating temperature and ambient temperature. Conductor dirting factors are applied to account for factors such as the number of conductors in a raceway, the type of raceway, and the ambient temperature. Using 500 kcmil conductors in a 3.5-inch rigid conduit, the conductor ampacity is 430 amps. The dirting factors are 0.91 for temperature and 0.8 for the number of conductors in a raceway. Therefore, service cable size equals 600 amps times 1.25 divided by 430 amps times 0.91 times 0.8 equaling 928 kcmil. You would need to use two sets of 900 kcmil conductors in 3.5-inch rigid conduit per set to meet the NEC requirement. To further clarify the National Electrical Code, or NEC, considerations for sizing electrical services, particularly in a scenario involving motors, transformers, and other loads, let's delve into a more detailed explanation of the relevant factors and calculations. Firstly, understanding continuous and non-continuous loads is crucial. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Non-continuous loads are those where the maximum current is not expected to persist for extended durations. Motors, depending on their operation, can be considered either continuous or non-continuous. If a motor runs for 3 hours or more without interruption, it is classified as a continuous load. The NEC mandates that the service capacity be calculated based on the sum of 100% of the continuous loads plus 125% of the motor full load current and 25% of the non-continuous loads. This requirement ensures that the electrical service has sufficient capacity to handle the expected load demands safely and efficiently. Secondly, the concept of rounding up to the next standard size plays a significant role in service sizing. After calculating the minimum service capacity based on the continuous and non-continuous loads, the NEC requires that the calculated value be rounded up to the next standard size of our overcurrent protection device. Standard sizes typically include 100, 200, 400, 600, 800, 1000, 1200 amps, and so on. This rounding up practice provides an additional safety margin and helps to accommodate any future load growth or unexpected variations in load demands. Thirdly, conductor sizing is a critical aspect of electrical service design. The NEC provides detailed guidelines for selecting the appropriate conductor size based on the calculated load current, ampacity ratings, and dirting factors. Ampacity refers to the maximum current that a conductor can safely carry without exceeding its temperature rating. Conductor ampacity is influenced by factors such as conductor material, insulation type, ambient temperature, and the presence of other conductors in the same raceway or cable assembly. Derating factors are applied to reduce the conductor ampacity to account for conditions that can affect its ability to dissipate heat effectively. These factors include ambient temperature correction, conductor bundling, and conduit fill. The formula for calculating the required conductor size is service cable size equals bus plug rating times 1.25 divided by conductor ampacity times conductor derating factors. This calculation ensures that the selected conductor size has sufficient ampacity to carry the calculated load current while considering the applicable derating factors. This helps prevent conductor overheating, insulation damage, and potential fire hazards. Fourthly, the role of transformers in the system must be carefully considered. Transformers are used to step up or step down voltage levels to match the requirements of different loads. When sizing the electrical service, the kVA rating of the transformers must be taken into account. The kVA rating represents the apparent power that the transformer can deliver. To determine the equivalent current draw of the transformers, the kVA rating is divided by the voltage level. This calculation provides the current that the transformer will draw from the electrical service, which must be included in the overall load calculation. Fifthly, motor contributions need to be accurately accounted for. Motors can contribute to the overall load demand in several ways. Firstly, the full load current of each motor must be included in the service capacity calculation. The full load current is the current that the motor draws when operating at its rated horsepower and voltage. The NEC provides tables that list the full load currents for various motor sizes and types. Secondly, the starting current of motors can be significantly higher than their full load current. This inrush current can cause voltage drops and other disturbances in the electrical system. To mitigate these effects, the NEC allows for the use of overcurrent protection devices with time delay characteristics such as in burst time circuit breakers or fuses. These devices can withstand the inrush current for a short duration without tripping, while still providing protection against sustained overloads and short circuits. Sixthly, practical examples and case studies can help to illustrate the application of these principles in real-world scenarios. Suppose a commercial building has a 480-volt, three-phase electrical service that supplies power to a variety of loads, including motors, lighting, and HVAC equipment. The building has a total continuous load of 300 kilowatts, a non-continuous load of 100 kilowatts, and 350 horsepower motors. To determine the minimum service capacity required by the NEC, we must first calculate the total continuous load. The continuous load is 300 kilowatts, which is equivalent to 361 amps at 480 volts, three-phase. Next, we must calculate the total non-continuous load. The non-continuous load is 100 kilowatts, which is equivalent to 120 amps at 480 volts, three-phase. Then we calculate the full load current of the 350 horsepower motors. According to NEC tables, the full load current of a 50 horsepower motor at 480 volts, three-phase, is approximately 65 amps. Therefore, the total full load current of the three motors is 3 times 65 amps, equaling 195 amps. Using the NEC formula, the minimum service capacity is 100% of the continuous load plus 125% of the motor full load current plus 25% of the non-continuous load, which equates to 361 amps plus 1.25 times 195 amps plus 0.25 times 120 amps, totaling 635.75 amps. The NEC requires that this value be rounded up to the next standard size, which is 800 amps. Therefore, the minimum service capacity required for this building is 800 amps. To determine the appropriate conductor size for the electrical service, we must consider the ampacity ratings of the conductors and any applicable derating factors. Suppose we choose to use 500 kc mil copper conductors with THHN insulation, which has an ampacity rating of 430 amps at 75 degrees Celsius. If the conductors are installed in a conduit with more than 3 current-carrying conductors, a derating factor of 0.8 must be applied. Therefore, the derated ampacity of the conductors is 430 amps times 0.8, equaling 344 amps. To carry the calculated load current of 635.75 amps, we would need to use multiple conductors in parallel. In this case, we would need to use at least 2 sets of 500 kc male conductors in parallel. 2 sets of 500 kc male conductors would provide a total ampacity of 2 times 344 amps, equaling 688 amps, which is sufficient to carry the calculated load current. Therefore, the electrical service for this building should be sized at 800 amps, with 2 sets of 500 kc mil copper conductors with THHN insulation installed in parallel. This example illustrates the importance of following the NEC guidelines for calculating service capacity and conductor sizing to ensure a safe and reliable electrical system. In summary, sizing an electrical service for motors and transformers requires a thorough understanding of the NEC requirements, including the classification of continuous and non-continuous loads, the application of directing factors, and the consideration of transformer kVA ratings and motor contributions. By carefully following these guidelines and performing the necessary calculations, electrical engineers and contractors can ensure that the electrical service has sufficient capacity to meet the demands of the connected loads while maintaining safety and reliability. Let's examine another scenario involving a commercial building with a 480-volt, 3-phase electrical service. This building houses various equipment, including 375 horsepower motors, 125 horsepower motor, 2 120-volt motors, and 2 transformers rated at 1.5 kVA and 3 kVA respectively. The system's rated values are 214 kilowatts, 244 kVA, and 310.5 full load amps. Firstly, calculate the current for each component. For the 375 horsepower motors, refer to NEC table 430.250 for the full load current of 3-phase motors. A 75 horsepower motor at 460 volts, which is close to 480 volts, has a full load current of 96 amps. Therefore, the 3 motors draw 3 times 96 amps, equaling 288 amps. For the 125 horsepower motor, the full load current is 34 amps at 460 volts. For the 2 120-volt motors, assuming each motor is 1 horsepower, the full load current is approximately 16 amps per motor, totaling 32 amps. The 1.5 kVA transformer supplies 120 volts loads. Its current is 1500 volt amps divided by 480 volts, equaling 3.125 amps on the primary side. The 3 kVA transformer also supplies 120 volts loads. Its current is 3000 volt amps divided by 480 volts, equaling 6.25 amps on the primary side. Secondly, determine continuous and non-continuous loads. The 214 kilowatt system rating is a continuous load, equating to 214,000 watts divided by 480 volts divided by the square root of 3, which equals approximately 257 amps. Assume the motors are non-continuous loads. Calculate the total load. The total load is the continuous load of 257 amps plus 125% of the non-continuous motor load, which is 1.25 times 288 amps plus 34 amps plus 32 amps, resulting in 1.25 times 354 amps, equaling 442.5 amps. Add this to the continuous load of 257 amps, totaling 699.5 amps. The nameplate amps of 310.5 amps seems low. This could mean the power factor is low. Now, account for transformer loads. The total transformer load is 3.125 amps plus 6.25 amps, equaling 9.375 amps. Add this to the total 699.5 amps plus 9.375 amps, which equals 708.875 amps. Thirdly, apply NEC requirements. According to NEC Article 430.24, conductors supplying several motors must have an ampacity of at least 125% of the full load current of the highest rated motor, plus the sum of the full load currents of all other motors in the group. In this case, 1.25 times 96 amps plus 96 amps times 2 plus 34 amps plus 32 amps is 120 amps plus 192 amps plus 34 amps plus 32 amps, totaling 378 amps for motor loads. As for the service entrance, the 214 kilowatt rating translates to 257 amps as calculated previously. Then, including other loads, 1.5 kVA and 3 kVA transformers, the total is approximately 267 amps. For the service size, it's necessary to consider the continuous load, which is 257 amps. NEC 220.18 indicates that for continuous loads, the overcurrent device should not exceed 80% of its rating. Thus, the service size must be at least 125% of the continuous load. 1.25 times 257 amps is approximately 321.25 amps. This value is lower than the calculated load from the motors. NEC 430.22 indicates the feeder conductors supplying a motor shall have an ampacity not less than 125% of the motor's full load current. The largest motor is 75 horsepower at 96 amps. 1.25 times 96 amps equals 120 amps. With 375 horsepower motors, 125 horsepower motor, and two 1 horsepower motors, the conductor ampacity calculation would be 1.25 times 96 amps plus 2 times 96 amps plus 34 amps plus 32 amps, totaling 378 amps. For the service, you'll want to base it on the continuous load plus the motor load. 257 amps plus 378 amps yields 635 amps. Given directing factors, you might want to select a larger service size. Fourthly, conductor sizing and directing. You're considering using two sets of 500 kcmil copper conductors in parallel, each set in a 3.5-inch rigid conduit. Each 500 kcmil conductor has an ampacity of 430 amps at 75 degrees Celsius. With directing factors of 0.91 for temperature correction and 0.8 for the number of conductors in a raceway, the adjusted ampacity is 430 amps times 0.91 times 0.8, resulting in approximately 313 amps per conductor. Two sets provide 626 amps, which isn't sufficient for the calculated 635 amps, not even including the 310.5 amp value that was given. Fifthly, service wire calculation. To calculate the service wire size based on the bus plug rating, the formula is service cable size equals bus plug rating times 1.25 divided by conductor ampacity times conductor directing factors. Given a 600 amp bus plug, service cable size equals 600 amps times 1.25 divided by 430 amps times 0.91 times 0.8. Service cable size equals 750 amps divided by 312.64 amps. Service cable size equals approximately 2.4. This result means that each conductor will carry 2.4 times the current, so you'd want to use at least 3 sets of 500 kcmil cables. Sixthly, conclusions. The 600 amp service isn't solely based on the equipment's full load amps, but on the minimum service capacity required by the NEC. The NEC requires 100% of the continuous load plus 25% of the non-continuous load, rounded up to the next standard size. The 600 amp bus plug rating necessitates a service wire size calculation that accounts for conductor ampacity and directing factors. You'll likely need more than 2 sets of 500 kcmil conductors, considering the directing factors and the NEC requirements. Review the NEC articles 220, 430, and 310 for the latest guidelines and requirements for service calculations and conductor sizing. In summary, accurately determining the service size and conductor ampacity involves a detailed assessment of continuous and non-continuous loads, motor contributions, transformer loads, and applicable directing factors while adhering to the guidelines outlined in the NEC.